Shear and moment in beams. When a properly supported beam is subjected to loads, it is going to deflect. Although such a deflection may not be visible, it does cause internal forces to develop in the member. Take segment AB of this simply supported beam. Under the applied load, the segment deflects downward. This deflection compresses the top part of the segment while stretching its bottom part. We say the top part is in compression and the bottom part is in tension. Imagine the beam consists of an infinite number of long fibers. All the fibers along the top part of the segment are in compression, although to a different degree, and the fibers along the bottom part are in tension. The fiber that lies between the top and the bottom group, however, is neither in compression nor in tension. I have shown that fiber in color green. Suppose we straightened the fibers without changing their new lengths. Then we can see that the top fiber is the shortest and the bottom fiber is the longest in the section. And of course, the middle fiber experiences no change in its length. We refer to the axis that passes through that middle fiber as neutral axis. The topmost fiber, since it is the shortest, can be viewed as having the largest compressive force acting on it, and the bottom fiber, since it is the longest, then must be subjected to the largest tensile force. The force acting on each of the remaining fibers varies based on its position relative to the top and bottom fibers. It is important to note that the fiber along the neutral axis carries no force. Here are the forces present at the two ends of the segment. From the direction of the forces, it should be obvious that they want to cause a rotation. These forces want to turn the right vertical plane in the counterclockwise direction, and these forces want to turn the left vertical plane in the clockwise direction. We can argue that this rotational tendency is being caused by an internal force, which we call a bending moment. Let's refer to this compression force as P1 and denote its distance from the neutral axis as D1. We can do the same for the other forces. So, associated with each force is a corresponding distance from the neutral axis. The bending moment is defined as the sum of the product of each force and its distance from the neutral axis. So we have a clockwise bending moment at the left end of the beam segment and the counterclockwise moment at the right end of the segment. This pair is referred to as a positive bending moment, since they associated with compression along the top fiber and tension along the bottom fiber in the segment. A negative pair of bending moments acts in reverse. It causes tension along the top and compression along the bottom fiber of the segment. Now that we have a better understanding of the nature of bending moment in beams, let's see how we can calculate it. Consider a simply supported beam subjected to the weight of a person. Assuming he is standing at the midpoint of the beam, we wish to determine bending moment in the beam 1 meter away from the right support, at point C. We start by determining the beam's support reactions. Here is the free body diagram showing 3 unknown forces. There are 2 reaction forces at the pin and 1 reaction force at the roller. We write 3 equilibrium equations, then solve them for the unknowns. Having determined the reaction forces, we are now in the position to calculate bending moment at C. To do so, we cut the beam at C, separating it into a left segment and a right segment. This exposes the internal bending moment at C. The moment appears in both segments. The one for the right segment is drawn in the clockwise direction, and the one for the left segment is shown in the counterclockwise direction. Note that each of these internal moments tends to compress the top part of the beam near the cut point, hence it is considered to be acting in the positive direction. We can calculate this unknown bending moment using either the left or the right segment of the beam. To determine the moment, we simply apply the moment equilibrium equation to point C. For the left segment, the equation is, solving it for mc, we get bending moment has a unit of force times length. So here we have the moment expressed in kilonewton meters. Of course, we could have calculated the moment using the right segment of the beam, which would have given us the same value for MC. Let's calculate bending moment at another point, say point D. We start by cutting the beam at D. Draw the free body diagram for either the left or the right segment of the beam. Then write and solve the moment equilibrium equation in order to determine the internal moment. In addition to bending moment, beams carry another internal force. We call it the shear force. It is a force parallel to the cross-section of the beam. To see why shear develops in a typical beam, consider segment CD. It is subjected to distinct moments at its left and right ends. This pair of moments causes compression in the top fibers and tension in the bottom fibers of the segment. Let's show the compression and tension forces acting on the fibers this way. Since the left end moment is larger than the right end moment, compression and tension forces at the left end are going to be larger than their counterparts at the right end. I'm going to refer to the total compressive force at the left side as Q, and use R for the total compressive force at the right side. So Q is greater than R. Also, let's use M and N for the total tensile force at the left and the right sides, respectively. Then M is greater than N. Suppose we separate the tension zone from the compression zone, like this. This separation exposes another internal force in the segment, a horizontal force that acts in between the two segments. Why does such a force exist? To maintain static equilibrium. Since Q is greater than R, then another horizontal force needs to be present for the sum of the forces in the x direction to vanish. We call this a shear force. Also, notice how H wants to rotate the top segment in the clockwise direction. The shear force causes a clockwise moment about the horizontal axis defined by Q and R. The same happens in the bottom segment. H wants to turn the segment clockwise about the axis, shown using dashed line. To prevent the rotation of the top segment, a pair of vertical forces, causing a counterclockwise rotation, needs to be present. These are also shear forces since they act parallel to the cross-section of the beam. I'm going to refer to this shear force as VT. We get a similar pair of shear forces in the bottom segment as well. Let's refer to them as VB. Then the total shear force at the left and right end of the segment is the sum of VT and VB. This shear force comes about because of the differential bending moment at its ends. We can easily determine the shear force by writing and solving the moment equilibrium equation like this. So at point D, the internal forces in the beam are. Note how these forces ensure that both the left and the right segments of the beam remain in static equilibrium. The sum of the forces in the y direction and the sum of the moments in both free body diagrams equal to 0. This makes calculating shear and moment in beams rather straightforward. We don't need to figure out the internal tension and compression forces in the beam in order to determine shear and moment. We can determine these forces directly from the static equilibrium equations. Consider a statically determinant beam subjected to two concentrated loads, like this. Let's calculate the shear and moment forces at the midpoint of the beam. We always start by determining the beam's support reactions. Here is the free body diagram of the entire beam, and here are the three equilibrium equations. Solving them for the unknown reactions, we get Now let's cut the beam at its midpoint, exposing the internal shear and moment at the point. Note that I am showing the moment in the positive direction here. Shear is considered positive if it wants to turn the beam segment in the clockwise direction. This means a positive shear shows up as a downward force at the left end of the cut, wanting to turn the left segment of the beam in the clockwise direction. The shear force at the right end of the cut then needs to be placed in the upward direction, again, wanting to turn the right segment in the clockwise direction. So, by convention, any time we cut a beam, we draw a pair of bending moments and a pair of shear forces. The shear force at the left end should be downward, and the one at the right end should be upward. The moment at the left end should be in the counterclockwise direction, and the one at the right end should be shown in a clockwise direction. Obviously, we can use a different sign convention here, but regardless of the sign convention being used, it is imperative to keep in mind that the internal forces at the left and the right ends of the cut must cancel each other out. So the two shear forces must act in opposite directions, and the two moments must act in opposite directions so that their sum ends up to be 0. Let's use the left segment to calculate V and M. Here are the two equilibrium equations. Solving them for the unknowns, we get We will continue this discussion in a future lecture. For now, see if you can solve the following problems.